You drop your phone on a pad and it charges through plastic. How? A cable pushes electrons through metal. Wireless charging skips the plug entirely. You set the phone on a pad and power flows through solid plastic with no exposed contacts. There is a gap between pad and phone, yet energy still crosses that empty space. Hidden under the pad is a flat loop of copper wire, a transmitter coil. Inside your phone sits a smaller matching coil, the receiver. The two coils face each other like partners in a dance, separated by millimeters of air. The pad does not shoot electricity through the air. It converts current into a magnetic field. The pad feeds its coil alternating current, AC, that reverses direction many times per second. In AC, electrons slosh back and forth in the wire instead of marching in one direction. That moving charge creates a magnetic field that pulses and expands around the coil. The field oscillates at a tuned frequency, often around 100 kilohertz for Qi chargers. Those magnetic field lines pass through the plastic pad and leap across the gap to your phone. Energy hops the air gap with no metal bridge, an invisible magnetic link. Both pad and phone agree on the same standard frequency, so the link stays locked in. Think of it like a carrier wave, but carrying power instead of music or voice. The phone coil acts like an antenna, catching the changing magnetic field from the pad. A changing magnetic field through a coil induces voltage. That is electromagnetic induction. Faraday's law, in plain English, moving magnetism through copper makes electricity appear. Magnetic coupling alone is not enough. Both sides are tuned to resonate at the same frequency. When the coils ring together, energy transfers far more efficiently than a mismatched pair would. Resonance works like pushing a swing at exactly the right moment. Small input, big result. Qi chargers need the coils to overlap enough. Alignment matters for a strong link. Set the phone off-center and charging slows or stops. The coils are no longer lined up. Metal objects on the pad can block the field. Eddy currents steal or disrupt the energy. A thick case or pop socket can weaken the link by pushing the coils farther apart. The phone coil still produces alternating voltage, AC, not battery-ready power yet. A rectifier inside the phone flips that AC into steady direct current, DC. That DC feeds the charging chip, which safely fills the battery. Qi also sends tiny data bursts back and forth. Pad and phone negotiate as they charge. They agree on how many watts are safe, when to slow down, and when to stop. Not every watt makes it through. Some energy turns into heat on both sides. Wireless is convenient, but a cable is still more efficient on most phones today. MagSafe adds magnets, so the coils snap into alignment every time you drop the phone on. Some phones can charge other gadgets too. Reverse wireless sends power from phone to earbuds. Researchers dream of room-scale charging, a transmitter in the ceiling feeding devices on a desk. Furniture with coils built into lamps and nightstands could hide the pad entirely. One zone might someday charge a phone, a watch, and earbuds at the same time. Physics still sets limits. Widen the gap too much, and efficiency drops fast. So wireless charging is really AC in a coil, an oscillating magnetic field, resonant induction, and a rectifier turning it into DC. Drop your phone on a pad, and you are riding invisible magnetism through plastic. Tuned coils doing the work. That's the core idea, explained in plain English. Want more hand-drawn explainers like this? Subscribe to Doodlemicro for the next one. One clear concept per video. Science, tech, money, and more. Thanks for watching. See you in the next Doodle.